here in the first session, we're going to do scheduling theory, basic job submission, and parallel computing and job submission. So I'm often asked, what is batch scheduling? So the way we use these clusters here is batch scheduling. Now, batch scheduling is not used when you need to run a service. For example, a web server that runs all the time. But it is the preferred way if you have more, one or more jobs that need to be run, and you wish to get the results back sometime in the future. So you have a simulation, you want it to be run. There may not be enough resources to start it immediately, but you'd like your job to start when there are enough resources for your job to run and get back to you. And you may have thousands of these potentially. So your job is automatically started by the scheduler when enough resources are available, and you get the results back. You may be notified when your job finishes. Any questions? Okay. So let's look at a typical HPC cluster. We have the internet. You connect from there to a login node. There is an internal cluster network that could be more than one. Maybe there's a high-speed one and a regular one, a management network as well. It has a number of compute nodes. In addition, you have some file systems. You have a scheduler node. The scheduler node runs the scheduler. It tells when to start the job, when to end the jobs. So it decides which job runs when. And you may have an administrative node. So the way you use a typical cluster is you log into the login node, you submit a job, the scheduler node figures out onto which resources your job can run, and then it tells those resources to start your job, and your job runs. So this is a simplified, typical small HPC cluster. I was assured that that would stop at 1. I'm sorry. So you can have a small HPC cluster. So some of these functions could all be the same node. You could have a login / scheduler / administrative node. So this would be typical if you had, 8 servers in a research group cluster, right? Even the file system node could be the same one. Or you could have a much bigger HPC cluster. So this would be something like closer to what Cedar and Graham are. You have many, many different other services nodes. Your file systems are fairly complex. Your file systems are complex. You have a Lustre file system. It's composed of many metadata servers and object storage servers. You have storage. You have different types of file systems, CVMFS, etc. So clusters get a little bit more complex than this. So I think Cedar and Graham are actually even more complex than this one, but the basic structure is still there. You log into the login node, the scheduler node starts your job, figures out where your job runs, and it runs on those resources. So any questions? Okay. So what are the goals of scheduling? Well, the goals of scheduling are, there's a few. So you want to be fair. So you want to schedule fairly, according to policy. So if it's determined that certain projects should have more resources, then you want to schedule according to that policy. So you would like to schedule fairly according to whatever policy that there is. Another goal is you want efficiency, utilization, and throughput. So you'd like to use all the resources in the cluster, right? You don't want anything sitting empty and idle. You would like every single bit of the cluster being used to generate new science. And your third goal is you want to minimize turnaround time. So you'd like to get researchers their simulations back as soon as possible. And these three goals are basically contradictory to each other. So we have to pick a happy medium between all these different goals. So a little bit about fairness in policy. It doesn't mean everybody gets the same, or every group gets the same usage. So unimportant science projects may get a larger allocation, and the scheduler allocates fairly to the policy. With efficiency, utilization, and throughput, we want all the resources. So not just the nodes, but we want the CPUs, the GPUs, the memory, the disk, software licenses, bandwidth, and more, all to be used simultaneously. So we'd like everything to be fully utilized. And we'd like to minimize how many gaps there are in the scheduling system between jobs. So you can imagine if one job uses all the memory on the node, but only a single CPU, the other CPUs are sitting empty, right? But we'd like to minimize this as much as possible. The other goal here is to minimize turnaround time. So you want your research to get back, your simulation to get back as fast as possible. So it's important for researchers that use an iterative process. So if somebody wants to run a job, get the result of the job, and run another job based on the result of this job, we want to minimize, if it takes too long, if it takes a very long time for a job to be ready, you're not going to be able to do very much science this way. On the other hand, other people have a very large number of jobs, and they care about running them all. So they don't have an iterative workflow. They don't mind this so much. But both of these are important, two different types of users. So now, let's have some insight. The shorter the wall time, so what the wall time is the maximum time a job will run before being killed, the better we can meet the goals of scheduling. So if jobs are short, then it's easy to pack them in tightly. Or it's easier to pack them in tightly. They're going to be more responsive. Users are going to get their results back quicker. And they're going to be more fair, because we'll have more chances to be fair. So we'll be more fairly be able to allocate according to policy as well. Another idea is that jobs using a large amount of resources per job result in a reduction of fairness, efficiency, and responsiveness. So if somebody wants to run a job that takes up most of the cluster, that means that the cluster is going to be very unresponsive to other people while that job's running. So what does it mean? Well, the more nodes we have, the better we can meet these goals. So what that means is that the larger the cluster, the more fair, the more efficient, the more responsive it can be for the same type of jobs. Larger clusters are also capable of running larger jobs that expand capability. So if you have a cluster with 30,000 cores, well, it could be set up to allow a very large job to run, a 30,000 core job to run. However, if you're going to run such large jobs, then you lose the advantages of the large cluster, right? If you increase the size of the jobs, then the cluster doesn't get, with the size of the cluster, it doesn't get more efficient. If we maintain the same size of jobs, then the cluster gets more efficient, more fair, and so on. But if we just make larger jobs, that doesn't help with the larger cluster. Doesn't change very much. But what it does mean is that shared resources, such as WestGrid or Compute Canada, are better and are used more efficiently than multiple small clusters. The larger scope of shared resources, the better. So these are advantages to having, a couple of clusters in Compute Canada as opposed to having 60 different clusters across the organization. We could be more responsive and better meet your needs. Okay. So let's visualize what happens in a cluster. So this is a single node cluster. We have 4 cores. So this is an example. It's an example of something that's quite a bit older than what's available right now. And that's because it'd be really difficult to show all 32 on a piece of paper. So we're going to show this simpler example with 4 cores. Notice at the top, there's a time from now up till 7 days from now. So here we'll see both jobs that are running right now and potentially what are going to be scheduled into the future, and for each core. We show memory here, but you can visualize memory quite similarly as well. Are there any questions? Okay. So here's an example with running jobs. Now you can see 4 running jobs here, and they end at different times. They're here in blue. So one of those jobs is going to end in a few hours. Another one will end before the end of the day. The job on core 3 is going to end somewhere in a day and a half from now, and the job on core 4 is going to end the third day from now. So here we can visualize the running jobs. Now, we're doing this so you can visualize what's going on the cluster and see sort of how Tetris-like this is. So here we have a number of jobs. The size of these jobs reflects their size. So job number 1 is a 4-core job lasting 3 days. Job number 2 is a 1-core job lasting 3 days. Job 3 is a 2-core job lasting a day. Now, let's assume that these jobs are numbered in order of priority. So job 1 is the highest priority job, job 2 is the second highest, and so on. Well, how would this system run? How would it run on a 1-core cluster? Well, the scheduling system, what it does is it schedules in order of priority. So it puts the highest priority job the very first place it can put it. In this case, it's going to start in 3.5 days. It can't put it any earlier because there's running jobs, right? And it can't take away those resources from the running jobs. So your highest priority job is starting the very earliest bit it can. Your second highest priority job. Well, it could fit in before the highest priority job because there's resources available. So in this case, it's going to start in a few hours. Your third highest priority job will fit in then. The fourth highest priority job will go in. Fifth and sixth. Notice that job number 1, the highest priority job, is actually going to be the last job that is going to be run. But there is no time that it could be run. There is no way we could do this so that it would run earlier. It has to run when there's enough resources, and that's the earliest we can make the system have enough resources to start it. So while job priority is important, it's also how many resources are available and how long it's going to take to gather those resources on a cluster. Also, another thing that can happen. Let's say a job finishes earlier. Let's say this job on core 4 crashes. Now, none of these other jobs have been scheduled yet. And the scheduling system has a scheduling cycle every few minutes. So it's going to check again. At this point, the jobs are rescheduled. So the highest priority job is scheduled. And the second highest priority job is rescheduled. Notice that the second highest priority job now is starting 4.5 days from now. It was going to start in a few hours. So this is why the time when, the estimates of when your job is supposed to start change. Because things change. Job finishes early, jobs crash, users submit other jobs, there's more higher priority jobs submitted before yours, or they're removed. Things change. And the scheduling system tries to make sure that your job runs as fast as possible, or in terms of priority, which is taken from trying to make the system fair. We'll discuss that later. It's probably going to be, what's it called, on the third day. In here we have the third highest priority job. Now this one is starting earlier than it used to as well. We go for job 4, which is the same place, I think. But job 5 and 6 end up being scheduled later as well. So are there any questions? So let's go back to the example before, without the job finishing early. Here's a little bit. Notice that there's holes here where there's no resources being used. So this is bad because we would like all the resources in a cluster to be used, right? We'd like all the cores to be used all the time to generate research. And here we have empty cores that are going to be sitting empty, that are going to be doing nothing. Now, what we'd like to do is if we had smaller jobs that could fit into those holes. Now, it doesn't matter what the priority of those jobs would be, because if they could fit in and there's no other use for those jobs, they would run. So if somebody had some short serial jobs, they could backfill. The short serial jobs can run in these spaces. It doesn't matter what the priority is. They would just run because no other jobs could use those resources because these are. So one of the first things that you could take from this talk is that if you have short jobs, or if your job could be broken up into a series of short jobs, you should do so. Because those shorter jobs, not only, since these since they'll be running in these holes in the system, other people, what's it called? You're not going to be stopping other jobs from running any later, right? We see these short serial jobs, these yellow, they don't actually make any of those other jobs run any later. They just more efficiently use the system. So if you can make a good use of this, if you can make your job smaller and fit in, everybody wins. So there's a few myths about clusters. Now, number one, if there's a large number of jobs in the queue, my job will not run quickly. Now, that's not true at all. So most of the time, the jobs belong to users with very low priority. So there's researchers that submit thousands and thousands of jobs. And they wish to see their results back when they get them back, right? But they can run way more jobs than their priority allows them. So they usually have low priority, they have a large number of jobs in the queue, and when their priority goes back up, some of the jobs run and so on. Now, most of those jobs may not be capable of running, as the number of running jobs per user may be limited. The cluster may even have empty processes available for immediate use. But deciding if a cluster is busy by the number of queue jobs doesn't work. So just because you see lots of jobs in the queue, you couldn't use the cluster. Another myth is it's better not to submit too many jobs at a time so that other users can run. Big myth too. The scheduling system is more efficient if you submit your jobs earlier, as long as you don't go over some usage limits that are very, very huge. The fairness is ensured by the scheduling system. So, being polite by not submitting jobs, that's no good. The scheduling system is actually more efficient if you submit your jobs earlier. So please submit your jobs and have the scheduling system figure out which job it should run next. So that's the most efficient. Are there any questions? By the way, this part of the presentation, it's the same one I gave about MOAP scheduling system as well. So what's true for MOAP is also true for Slurm here. It's basically how all the scheduling systems work. So some tips. Well, one is make sure your job can run on the resources available on the cluster. So if you ask for more memory per node than is available in the cluster, your job will never run. And the scheduling system will think, well, maybe a system administrator is going to expand the cluster, so we'll just let your job sit there forever, hoping that somebody will install more nodes with more memory. So make sure that your job actually can run on the resources available. Look at the state of the cluster, your job account, and the jobs to get more information. And if the cluster is empty and you are able to run shorter jobs to evade some of the limits. So sometimes in clusters, there's limits that prevent the first user that jump onto the system from taking over the whole cluster, or at least taking over the whole cluster for a long time. However, if the cluster has crashed and it's sitting empty, you may be able to get the whole cluster, but only for a short period of time. So somebody, number of shorter jobs may get your jobs run. Is there any questions? Okay. So we'll start with basic job submission in Slurm.
Sorry, I have a question actually.
Okay.
So basically, my question is, is there any reason why a job might be canceled once it started to run?
Well, it could crash, right? So the job could crash, so that's one reason it could be canceled. Another one is that you could cancel it directly.
But other than the user canceling by themselves, or something happened with the job and crashing, is there any other external reason for the job to be canceled?
Yes. So for instance, if your job is really, really big, uses a lot of nodes, it's possible that one of those nodes has a problem, right? So if your job is running on 1,000 nodes, there is a good chance, especially if it's a longer job, that one of those nodes will break. Because now you're talking about many thousands of disks, many thousands of CPUs, thousands of sticks of RAM, that sort of thing. Computers fail, right? So one is the hardware fails, or you have a file system problem. So potentially, if there's a hardware or software issue with the cluster, or a power issue, or a cooling issue with the room, right? So any of those can cause your job to fail. Yeah. Or potentially, if your job is doing something really bad to the cluster, it's possible for a system administrator to what's it called, stop your job. Or another thing that may happen is if, say, we're having a cooling issue. So let's say that the air conditioner is dying and the room is going to be overheating. So a system administrator might come in and kill jobs and shut down nodes because they have to do it for the cluster to survive. So that's another scenario where this happens.
Okay, is that something that could happen pretty often?
No. So the data centers run for weeks and months between issues, right? But there are storms, there's power outages, and that sort of thing, right? They do happen, every few months.
Okay, that's great. Thank you.
Okay. So for submitting a job, if you have a program that you wish to run, you need to figure out the amount of resources that your job requires. So these include the wall time, which is the maximum length of time your job will take to run, the number of CPUs, the amount of memory, the number of nodes, the number of GPUs that you require. Also the partition you're submitting to in some clusters. So you need to figure out what you're requesting, how much resources you're requesting for your job to run. So the command to submit your job is sbatch. Although sbatch allows you to specify your requirement on the command line, you should put your requirements in a job script. So an example here would be sbatch jobscript.sh. Usually for Slurm, people end their jobs with .sh. For MOA, people used to end it with .pbs. It's convention. So let's look at a simple job script. You have a number of things here. You have a #bin bash. This is which shell your job's running in. Then you have a number of other pieces. Number of tasks. So a task is sort of a container, a thing. So you can divide your job into pieces. You could have a number of different tasks. You could have a number of resources per task, like cores and so on. You could also have a number of nodes. So nodes are basically servers. You could also request cores and so on. By default, you have one core per task. You can request how long your job is supposed to run. This one's 2 seconds. Or 2 minutes. You can request when your job will mail you. So if it will mail you when your job starts, when it finishes, when it crashes, all this sort of thing. The email address that your job will email you at. You also want to have a job output file where your job puts output by default. You may want to specify a job name so that when you look for your job, you can see it by name. And in this example, we have sleep 1000, which is just do nothing for 1,000 seconds. But you would replace this line with the line running your code. So in all this just describes the amount of resources that the scheduler will give your job. It doesn't actually tell the job how much resources to use, although by default, it sets certain environment variables inside of your job, and it's possible that the job may actually know about those environment variables. So whatever program you're running, it may know about those environment variables and use as many cores as the scheduling system has reserved for it. But in here, fundamentally, this is just describing the amount of resources that the scheduling system will give your job. So any questions? Okay. to here. So along the other documents that you have for this course, there is the Slurm script one. It includes all this stuff in a separate document, so you don't have to go through the 175 pages of the regular one, of the regular scheduling presentation in order to see the parts that you need to look up. So it's a separate document that you could look up quite easily. Is there a question? Okay. So once again, n tasks, number of tasks. So it requests one processor or one core per task usually, unless you set it otherwise. This is how you get 5 hours of maximum wall time. Also, you could put in different settings. So if you wanted to email you when your job begins, when it ends, when it fails, it's requeued, or every single time. You could do that. So is there any questions? Okay, because we're going to move sort of to another bit here. So Slurm jobs and steps. So unlike PBS, unlike MOAP, Slurm jobs can have multiple steps. So each of these steps is like a job and may have multiple different resources in it. You could use the command srun to carry out each step. Srun has a similar syntax, so its language is quite similar to sbatch. And you can have a prologue and epilogue per step. So a prologue is a script that runs before your job or your step, and an epilogue runs after it's finished. We'll talk about prologue and epilogue scripts later. Any questions? Okay. Unlike, interactive jobs. So you can ask for an interactive job to run a program on a cluster and interact with it while it's running. So interactive jobs are very useful for debugging. But to request and use an interactive job is a multi-step process. So you could request an allocation of resources with the salloc command. Its syntax is somewhat similar. So you can do an salloc. You could do an salloc. You could do an salloc minus n tasks, which is number of tasks, minus node equals 1, and a time. So most of those things you had with the ability to request, they're available in salloc just as they are available inside of sbatch. You could proceed to open a shell inside the allocated job with srun. So srun minus pty minus p interactive bash. On Cedar and Graham, this is done automatically for you. But on other machines with Slurm, it's possible, but you need to actually specify the interactive session. So salloc just allocates the job on most systems, and then you need to do an srun to get actually into the job, because you're still on the head node. But on Cedar and Graham, this is done automatically.
What is the default memory?
Oh, it's very small.
So if the job violates any of these resources, then they might be killed by Slurm too, right?
Yes. Depends how. So there is mechanisms called C groups that prevent you from stepping onto some other job's memory. So it's possible that your job is just going to not have enough memory and it's going to thrash because of it. So it will try to write it to disk or something like that, or crash by itself. So some operating systems have the ability to box your job into the resources that you've requested. So I actually have an example of this later. Any other questions? Okay, so there's a question. Is it possible to request a huge amount of RAM for interactive jobs just for testing? It's possible if there is a node with that huge amount of RAM available. So when you're asking for an interactive job, you're asking for an empty node. So we do have a certain amount of nodes that are reserved for interactive usage, sitting empty, not running other jobs, just so that people can test. But there's not a lot of them, and they tend not to be the huge memory nodes. Now, your job can run on those huge memory, your interactive job can run on those huge memory nodes, but they have to be available quickly, right? Because if you want to run an interactive job, you care about it being available now instead of, say, 13 hours from now.
So one question. This is what we should do in order to kind of test our jobs before submitting them, like, for example, to know how much memory or how much time we need for a specific job. We should be using this type kind of and kind of allocate an interactive job.
Well, an interactive job will give you some information on the number of memory you need. Also, you could work out how you schedule the job, how you run it, and so on. But the interactive resources are only available for a short period of time to stop people from trying to run real jobs in these resources, right? Because if they did that, then they wouldn't be available for testing.
For example, if I need to run a job and I have no idea how long it can take, I can kind of run a sample job on this as an interactive job and get an idea on how long it will take to run.
Well, you can't, because there is a limit. I think it's under 3 hours for the interactive jobs. So okay. It won't let you run a very long job interactively.
Okay.
So we have a question. Won't OS use a page file or virtual memory in case of a large memory request instead of insufficient memory error? So yes, it's possible that the operating system, if you use more than you request, will start memory paging. But eventually that may cause, well, a number of things. That will make your job extremely slow, because any program that page faults, going to disk is thousands of times slower than going to memory. And second of all, it actually causes problems for the operating system as well. And some of those problems the scheduling system sees, and if your job is destroying the node it's running on or causing it issues, your job will be killed. So you should try to ask for the amount of resources that you need. Hopefully that answered the page file question.
Just a question. The Slurm doesn't kill the job because of the memory that requested, that the job is used, like it's more than the requested memory?
So Slurm job will do that, except that there is a mechanism. So there's a C group mechanism in the operating system that will actually prevent your job from using more memory than you've requested.
But then the Slurm should not submit that job at the first place, right?
Well, okay. So when you submit a job, you're asking for a certain amount of resources, yes? So Slurm will create you a reservation with enough memory with the memory that you've requested. Now, if your job uses more than it requested, then it will be inside a C group that will only have the amount of memory. So the operating system has this C group mechanism that will prevent your job from using more memory than it requested. And it will try to page file, actually. It will go to virtual memory. It will try to use the disk. But that will cause issues, potentially. And if it causes enough issues, the Slurm will kill your job. Did that answer your question?
I just once submitted the interactive job. The node was totally empty, but my job killed because of memory that I have used. It was more than requested memory. It wasn't killed by the OS. It was killed by the Slurm.
Yes. There is both effects happening. So the scheduling system always was able to do this. But the operating system also keeps the jobs apart with the C groups. And the scheduling system checks on what the operating system is doing as well.
Okay.
So previously, especially for larger jobs, it was quite possible for one job to run on the resources that another job requested, right? It's more difficult now with C groups.
Yes.
Any other questions? Okay. So you should be also aware that Slurm, when your job runs, has environment variables that are set. So environment variables are variables that are on the system. So you could do something like print env to print all the environment variables that are currently here. For instance, log name, which is my login name, but there's many. So there is a, what's it called, compute kind of cluster variable called Cedar. But the scheduling system has special environment variables inside your job. So for instance, your job's name, your job's ID, number of nodes it uses, the number of tasks it has, its array task ID. And so we'll go into some of these other ones later. But you should be aware that there are environment variables that are set. So if you're running a job and you need to control it, there's ones here. Okay. So now we're going to go to the scheduling worksheet. And here we're going to be tasks with a few questions. We're going to go through and start submitting some jobs. And we're going to go through the first 6 questions. As well, you should be aware, if you copied the directory, that there's actually answers available as well. So if you're having issues, if you don't understand, you could actually also look up the answers. Some of these questions eventually are going to also require some starting points or some programs. They're available inside this tardoc directory as well. There's another question in the group chat. So what if I increase the required memory with the dynamic allocation during my job runtime and continue if the allocation succeeds? Is it going to work for preventing the crash? So as a user, you can't ask for more resources once your job starts from the scheduling system. The scheduling system, what's it called, makes assumptions that jobs are going to be forever the size that they were when, or smaller when they were requested. So, for instance, because otherwise it would not be fair. So, remember going back to here, if somebody requested a certain amount of resources for job 3, and then made it a lot larger, say take a lot more time, then it would stop the higher priority job from running. So we can't do that. So users are not allowed to change the size, make their jobs longer, make their jobs bigger once they're started. So we'll start with the first 6 questions. If anybody has questions, please feel free to speak or to put it into the group chat. Oh, yes. I forgot one thing. So during this talk, there's a reservation that was created. For all the people that are in this workshop, the reservation is called Workshop. So if you add, when you're submitting your jobs, if you add an sbatch minus reservation equals, and then the reservation name, in this case, Workshop. This is a special reservation that other people cannot run in, only the participants of this workshop. So it should be really fast to run your jobs, as opposed to potentially waiting a few hours. Now, waiting a few hours may be normal during regular work time, but we'd like to see the output of our test examples. And they tend to be short, so So here's an example of how we would put in the reservation. Also, if you get an error such as this, that may be because you have multiple CPU allocations on you. You may have to specify which allocation to use. Most of you will not have multiple allocations. But some of you will. We talk about allocations a few minutes back. Okay, somebody was disconnected. They were asking, so where are we? So we've started looking at the running the jobs. So there's the worksheet, and it asks you to run a few jobs. The first 6 questions. So when you run a job, you get back a job ID. We'll look at these commands later, but you could do an SQ, and you could search for your job. The SQ will show you all the jobs that are queued, some information about them. Of course, it won't do so if your job is finished. Yeah, for those which are absolutely unable to create their own jobs, it's also possible to look at the answer sessions and run jobs and look at the results. Yeah, but I would recommend that you at least submit a few of these beginning jobs. If anybody's actually done, please type into the group chat that they're done, so I could see, the progress of the group as well. Any questions? Okay. We have somebody that says they're done. I wonder. Okay. When you say you're done, does that mean all the questions or just question number one? And somebody says they're not receiving the emails for the job so far. None at the end either. So you have to both put in your correct email here, right? So the email address here is just a dummy email address. You have to put it in your own. And you also need minus mail. So minus mail minus type equals all. So that should start your jobs at the beginning and when it fails. So people are receiving email if they have both sets, both put in their appropriate email and also tell their jobs to start stuff. So we're asked, what does the PD mean in the SQ output? In which PD? Oh, state. Yeah. So SQ actually has a lot of options. To view. You could look at it in man SQ, but PD means pending job. So your job is queued, but it hasn't started yet. It's going to start. There's R for running, CA for cancelled, and so on. You can make it say the whole word if you change the options for SQ. Yeah, -L gives you the long form, and it says pending. But there's a lot of options you could give SQ formatted. So we have a question. Can you provide a scenario for using n tasks greater than 1? Of course. So when you have an MPI job, when you have a parallel job, that would be a scenario where you increase the number of tasks. So as soon as we get finished with these 6 questions, these 6 ones, we're going to start talking about parallel jobs. So right now, all we're doing is running single core jobs, but we're going to start using parallel computing and out of request a larger number of jobs, or a large number of cores, sorry, for the same job. So more cores. Okay, but someone says it has no relevance in 0 jobs. Right, yeah. Basically, yes. I mean, n task is 1 for 0 jobs by definition, because you only have 1. If people could put into the group chat the last answer that they've answered, actually. The number of the question, or the last question that they've done. So if you guys could put the question you guys are working on in the group chat, that'd be great. Is there anybody that's done? Okay. Uh, I know a lot of people may not be quite done yet, but we're going to have to actually go through some of these answers and continue on. There are the answers available to you for all these questions. In the tar file, right? You just have to untar it. As we said earlier, if you want to use this reservation for the workshop, you have to add that in. You may have to put in the accounting group that you need to use if you have rack allocations, for instance. We'll talk about this later. But we're going to start going through these answers here. So in your first Cedar job, you're just asking for one core. You want to get emailed. You're asking for wall time 2 minutes, and you want to run the hostname command. Now, the hostname command just basically tells you which machine this job ran on. So here's what you would do. You may ask for just one task, one node, 0 job, 2 minutes runtime to get emailed when it begins. At all cases, begin, end, and fail. In this case, you want to run inside the reservation, but this is just a special case that we have a reservation for this workshop, so we can run quickly. In my case, I have multiple accounting groups, so I need to specify which accounting group I'm using. If you have that, the system will fail if you don't have this, and it will tell you what to put in here. And you should edit it so that your own email address is to the -- mail user. Also, you're supposed to run the hostname command that shows you the hostname. By the way, had anybody finished all the questions before we started, or? Okay. So we submit the batch file. If we run it quickly enough, well, it finished. Although we gave it 2 minutes to run, it didn't take an entire 2 minutes just to run hostname. So by this time, it has already finished. Now, when it started, it had the job ID, so that was 209.1619. And you see here, we have an output file. And the output file is the command that was run, the output of the commands that were run in there. The output of the commands was just hostname, and the full hostname of the node it ran on was Cedar 308. So you should have gotten something like this. So every time one of your jobs runs, you should get an output file. So second question. In the second question, you're also asked to run a 0 job. It also must email you when start, ends, and aborts. Has to have a maximum wall time of 2 minutes, run hostname. But we wanted to write standard output and standard error into separate files. And to look at the job ID of your job when it starts. To run an SQ - U, your username, and S control show job in your job ID. Okay. So the big additions here to the last one. So if you can take the previous one and just edit it a little bit. You could add an output file. In this case, we'll call the output file slurm-q1. Actually, it should be q2 for this one. It's the second question. And then the job ID. this little %J will be the job ID. We also set up a sleep, so sleep for 30 seconds. Give us some time to watch it be running. So we submit the job. We should be able to see it running in state R. And we want to run S-control show job. And then the job ID. And we see a large number, a big output here. So there's all kinds of information about your job that's running. So you have your user ID, start. Who are you? What's happening to the job state? How long it's been running? How much time it has left? When it was submitted, and so on. How many resources that are using? There's lots of information in here. So we'll be when we're going to be discussing S-control, we'll talk about all this information and what it tells you about the job, and how you could use this command to manage your jobs and understand what's going on. Yeah, does S-control only work while the job is running? I think so. I think this is one of those commands that only runs during that time. So if you would like to see the whole list of commands, in that Slurm script one, there's a table of all the commands, all kinds of information about canceling your job, looking at your job, getting all kinds of information after your job has run, and so on. So we'll be going over these at a later date. Now we see that this job is finished. We see here the output files. There's an error file, there's nothing in there. Output file just has the host name. So we've separated the error and the output file. So for those people that want to do that, that's how you do it. The answer is question 2. So question 3, zero job errors. So we'll submit a zero job. Now it requests a single core. It emails you when it starts, ends, and aborts. It has a maximum wall time of 2 minutes. Runs the hostname command. Writes, different standard output and error files. Runs a non-existent command called hello. So just, instead of having a sleep, you just put in hello. And let's see what happens. So here's what we have. Basically the same thing as last time, except now we have hello in there. So this just shows you what happens when you get an error. Running. And now we see it's actually finished because there's no output file. And here in the error bit, we see command not found. Hello, command not found. and nothing in the output. So this is the standard error. If you have something that fails, if your job has an error, you should be able to see it in the error output. Unfortunately, the S control is probably finished. So this information, oh, you can still get it. S control information goes away after a while, so you have to look at the other commands to see what happened. But we see that this job has completed. And some more, yeah, tells you what the standard error. If we wait a while, the S control will not work. So it's no longer available right now. So we'll go to question number 4. It's the same stuff that happened in question number 3, but here it's wall time. We ask for it to sleep for 200 seconds, but we have a maximum wall time of 2 minutes. So basically, this shows you what happens when your job exceeds wall time. So we set the runtime for 2 minutes, and we have a sleep of 200 seconds. Now we've submitted this job. It's running. And we see this job's running. Now, truth to be told, depending on which cluster this is happening, sometimes this actually doesn't fail because the scheduling system sometimes checks, whether your job is running too long, but it doesn't check every second. It may check every few seconds, and depending upon the cluster, your job actually may not fail. But it should work here. So we'll have to wait another 55 seconds. You'll see this job has crashed. Does anybody have any questions? So we see time has run out. And we actually see the reason. So it was cancelled, and the reason is doesn't quite say that anymore. It disappeared. But the reason is time limit. output. There's nothing. The error, and there is an error here. Cancelled at this time due to time limit. So if your job needs to run longer and you don't ask for long enough time, it will be killed. And you'll get an error like this. You should also look at your email. You will see inside your email information about the job and the fact that it was killed and the reason why. Okay. So let's start job number 5. The big thing about this one is it actually has a name. So some people like to name their jobs, to have a name to refer to their job by, not just a job number. But there we go. Minus job name, job minus name equals, and then the job name you wish for your job to start, or to be named. So now when you run SQ, instead of only a job ID, you also have a job name. So you can identify it more easily. I think you might be able to. If you run S control, you can actually also see it there. Or maybe not. You could get more commands for S control to actually give you more information as well. And if you look at the output, it's the same. Question: if a job is submitted with -N1 and both a capital and so let's look at that. So if it asks for N1, lowercase 1 is tasks equals 1. Is minus capital N1 the node? So some of these, yeah. Yes, so if somebody asks for minus N tasks equals 1, minus nodes equals 1. In that case, that's a serial job. That's just asking one task and one node. So that's exactly the type of jobs that are in this example. They all ask for N tasks equals 1, nodes equals 1. So these use a single core. So if you ask for both, you don't get a full node. You just get a single core. So it's one task on one node with one core. So we'll actually be able to see some of that inside here. So here on question number 6, we're going to go for an interactive job. So we're going to ask for 20 minutes of wall time, an interactive job. We'd also like to be emailed when it runs, ends, and aborts, and we'd also like to have its name my first interactive job. So how do we do that? Well, actually, we have an answer for that. We run salloc. Nodes equals 1. We give it a name. We can also have it email us. Yes. And if you have multiple accounting groups, once again, you have to do the same thing as you need to specify which one. Most of you won't, but I do. Yeah. The job was looking for resources. It was granted those resources. And by default, as I said, on Cedar and Graham, we actually put directly into the node. So here, we can actually see we are on Cedar 552, where previously we were on Cedar 5. Notice something else. This is unlike MOAP. For an interactive job, we're still in the same directory we were before. So in this case, the interactive job has inherited the same directory. If this was PBS, you would go into the default directory, not the one that you submitted your job from. So for quite a few of these things, actually, I wrote a script that gives us the answers, so I don't have to type in quite as much while I'm giving this presentation. So first of all, to run hostname, which node do you want? So that's hostname. We could look at all the environment variables for Slurm. So we print them and we grep for Slurm. We see a whole bunch of environment variables here, which node we're on, and so on. So if you had to run this on a cluster that didn't put you directly into the interactive node, you would have had to actually specify and run the srun minus pty to actually get the interactive node. But on this cluster, we're automatically put into there. So it's quite nice. You don't actually have to do that yourself. So we could echo Slurm node list. It shows us the list of nodes that this job is running on. It's Cedar 55. We're asked what is the job's name. We could echo Slurm job name environment variable, get them our my first interactive job. once again, we're noting which directory we're in, that we're in the same one that we submitted from, which is different from the other schedulers. And we can look at the execute path. So this is the path that's available for your job. Part D, we don't have to do because we're already inside the interactive partition. Part D is quite similar. If we run these, it's the same thing again. The purpose of doing this twice originally was that the interactive job didn't actually put you into the node that you were running. It just allocated the resource. But by default, you're now put into the resource. But we can actually look at your job. So you can actually see that my job is running. You can see my first interactive job. You notice that it's cut off. So a lot of these things may be cut off in the middle, depending upon your SQ option. So if you have a really, really long name, you won't see it. If you searched for like my first interactive job with grep, you wouldn't actually see it because the name is cut off at a certain number of characters. S control show job. Yeah. We can see that our job is running. It started 5 minutes ago. So are there any questions? By the way, this interactive job here, it shows you what's going on. So the scheduling system sets these environment variables, even in your job that is running without being interactive. So sometimes we set up MPI to actually read these environment variables, look at these environment variables, and then run your job appropriately. So if your job, if your script, if your program knows how to talk to the scheduler, it does so often via these environment variables. So we want to get the list of node names for each process of this job runs. Well, we could just echo Slurm job node list. Now, since we're only running on one node, it's quite simple. We could ask how many nodes does this job run on? And we could either echo Slurm job num nodes or Slurm n nodes. If we wanted to know the total number of tasks of this allocation, we could echo Slurm n tasks or n procs. If we wanted to see the number of tasks per node, it's Slurm tasks per node environment variable. How many steps there are? Well, it's echo Slurm step num tasks. Now, if we were running interactively, we could have requested a big allocation, run interactively, exited out of the interactive run, or exit out of the job that we were on the node, and then run another set. But in here, we're just doing it all as one step, so if we exit, we actually exit out totally. But had we done it in pieces, each of those would have been a separate step. And there is no job array ID. So if we echo Slurm array task ID. There is none. So we're going to go to a little bit of advanced Unix here. Now, a lot of people don't do this, but this is how the scheduler and the operating system control the resources on the node, on the cluster, on the server that you're running. So it's done via something called CPU sets and C groups. So basically, CPU sets C groups stop your program from running outside of a set of resources, whether it's memory or RAM or GPUs, that sort of thing. And we can actually see that there are actual directories based upon your job ID and your step and your username that are created by Slurm. And you could actually see which cores, how many cores, and which cores, how much memory and which memory your job could run on. Not only that, you could actually do echo $, which is your task ID. In this case, 147271. And we can actually see whether that is actually in the tasks that are running. And we see that it is. So we can tell that our shell is right now running inside this C group. And if we try to use more memory or more resources than are allocated to this job, the operating system will not let us. And then the scheduling system will come along sometime later and kill our job if we try to use more resources than we should have. We can even tell which cores and which resources. So show which cores in which memory set and which your job is running on. So, I mean, we could just grab this very long one, but it's CPU 6, and it's memory set 0 and 1. So in this case, if we try to use a CPU which is different from this, the operating system won't let us. So even if we set up a whole bunch of interactive things here and try to use many, many cores, all of that would run on CPU 6. And all of that would run within this memory set. But this is just a little bit of a more advanced Unix things. This is how it works. You don't have to understand this unless, this is more advanced things. Is there any questions for any of this now? Okay, can anybody hear me? Because I'm not getting any response. Okay. Okay. So we're going to talk about different job types and parallelism. So there's basically you can think of 4 different categories of parallelism. One type of parallelism is just running a lot of zero jobs. Another one, so that's a serial type of job, right? Another one is you could run MPI, many, many different processes, each requiring 1 CPU. You could run using many cores on a single node. So these types of jobs are OpenMP and Gaussian. And then there's hybrid types that require both. So we're going to visualize this just like we did before. So here is a multi-node cluster. We see that there's some jobs running on it in dark blue. We have 3 nodes, each with 4 cores. And then we'll see how each of these different types of parallel jobs are visualized in the cluster. So many serial jobs. Well, many serial jobs, there's 4 serial jobs. They're all 4 days long. And you can see some start earlier than others. And they start as fast as possible, as each of them can. In each of these examples, we're basically trying to run 4 cores for 4 days, but in different ways to show this difference. So many serial jobs. Well, each use 1 CPU per job. It's the easiest and most efficient to schedule. You have excellent scaling, so if you run 4 jobs, well, you get 4 times as much work done. So an example job would be parameters search. In your Slurm file, you could ask for a serial job with, sbatch and task equals 1. You could run many of these. So once again, this is the same example we had before. So tips for running more serial jobs. Submit shorter serial jobs. Many short serial jobs will run before longer ones. Oh, have we overrun our time? Yes. Okay. I see. Yes, sorry. We will, I guess, then continue on tomorrow. Maybe we'll just finish this short serial job, the serial job sessions of parallel jobs, and we'll continue on tomorrow with tomorrow's session. Yeah. So, some tips for running more serial jobs. We checkpoint larger jobs and submit them as shorter jobs. This will save you when a cluster suffers hardware or power failure. So if your jobs are really long, that's a problem. Okay. And one way of submitting jobs, short serial jobs, well, serial jobs is a job array. So jobs arrays are used when you need to submit a larger number of jobs using the same job script. There's a naming convention for jobs in an array, which is useful. So you have a job name and a job number, job array ID. So job arrays are preferred when you don't require as much. Oh, they're much faster to schedule because they're all the same size. So the scheduler only has to check 1 instead of 100 of them. You could submit the job with a sbatch minus array equals 1. This is like 0 to 99, which will give you 100 jobs numbered 0 from 99 with a single job submission. You can ask for a specific index. So in this case, your job will start with 1, 2, 3, 5, and 7, all the indexes. And you can also specify that only a certain number of jobs can run at the same time. And here's the job array example. Yeah. So I guess at this point, we'll stop and we'll continue on tomorrow.